What happened before the Big Bang? What actually is the Big Bang and what triggered it? In modern physics, we've been dealing with these questions for decades and are trying to understand the universe in a unified model. In this video, you will learn about a new, comprehensive theory that provides answers to these questions. Before we get into the details, let's get a quick overview. We will first establish a dynamic foundation in the form of a nonlinear spinor equation. We will refer to this as the fundamental interaction, or basic dynamics. With the help of the basic dynamics, we can then construct a more complex structure, the so-called preformation structure. This is the core concept from which all other physical structures in the universe will later emerge. First, however, the primordial universe will develop, essentially a tiny universe consisting of just 6 elementary particles, one of which will play a special role. This primordial universe will trigger a reproduction cascade that will produce an enormous number of elementary particle sets as a result. Here we distinguish between two different elementary particle sets. Sets depicted as small white boxes with a breakup line each contain elementary particles that we can assign to normal matter and antimatter. Sets without a breakup line contain elementary particles of dark matter. Immediately after the completion of the reproduction cascade, the earliest universe forms, which has a quantity ratio of 2/3 dark matter and 1/3 normal matter as well as antimatter. Space-time, however, does not exist yet. Measurements have shown that by the time of decoupling, about 380,000 years after the Big Bang, the proportion of dark matter and the proportion of normal matter as well as antimatter had already decreased. The change in this ratio becomes much clearer when you look at the composition of the universe today, which only consists of about 26.8% dark matter and just 4.9% normal matter and antimatter. In contrast, a considerable proportion of dark energy has built up, accounting for about 68.3%, which was not present at all in the earliest universe. So the question arises, why, and above all, how did this transformation occur? The reason for this redistribution are annihilation processes of dark matter as well as normal matter and antimatter. As a result, the proportions of dark matter and normal matter antimatter are constantly decreasing, and in turn, dark energy is building up. As we will see later, space-time structure is created simultaneously, which is a byproduct of the annihilation processes. This also means that space-time did not exist a priori, but only emerged as a secondary product of annihilation processes. The explosive rollout of space-time is ultimately what we commonly refer to as the Big Bang. But let's begin with the first step and derive the dynamic foundation. The building blocks of the foundation are the components of the two spinors psi and psi bar. In our case, these are Dirac spinors with 4 components each. We call the individual components of these spinors basis spinors. Spinors are the most generic mathematical objects, from which scalars, vectors, tensors, and more complex structures can be built through product formation. That becomes clear later in the creation process of elementary particles, which are not given as such, but are the result of a strictly fundamental construction and formation process. This means that elementary particles have a substructure of even more fundamental building blocks, the basis spinors depicted here. We've numbered the basis spinors from 1 to 8, so we can see how they are integrated into the fundamental interaction that is yet to be defined. Since the construction process we want to describe is fundamentally dynamic, the basis spinors exist only in a strict nonlinear interaction. This interaction must have the simplest possible structure, because if it had a more complex form, it could be decomposed and would therefore no longer be fundamental. The equations are d sigma alpha psi of x is equal to psi of x minus sigma alpha, psi bar of x, psi of x plus sigma alpha. And d sigma beta psi bar of x is equal to psi bar of x minus sigma beta, psi of x, psi bar of x plus sigma beta. The interaction is initiated by the differential operator d and takes place at the interaction point x, which is subject to a certain degree of uncertainty. This uncertainty is described by the point split and exists due to the fact that the interaction cannot take place at a fixed point. The interaction depicted here automatically contains the differential operation d is equal to d dx, and in turn with dx the point split sigma alpha or sigma beta. The point split is therefore nothing other than the dx and is present on both the left-hand side and the right-hand side of the equation. Point splits will play an important role as they contribute significantly to the formation of individual particles. We will look at this in detail later. For now, it is enough to know that more complex spinor products can contain several point splits, which occur in two different states. If the point splits open up, then they are unequal to zero, and we speak of a system opening phase, which in turn leads to a point split separated local environment, or to put it more simply, to an open system. If the point splits tend to zero, we speak of a system closure phase. If the limit of zero is reached, we refer to the system as closed or fixed locally. Individual particles and their properties will emerge during the system closure phase, and they can then eventually be identified in the closed system. This is all we need to build more complex structures in the following. Before we do that, I would like to say a few words about the length dimension of the basis spinors. The length dimension of a basis spinor is -1/2. This means that the basis spinors are not observable quantities and therefore only exist in the interaction described here. As we will see later, observable fermions have a canonical length dimension of -3/2 and must therefore be psi-3 objects, meaning a product of 3 basis spinors. Observable bosons have a length dimension of -1 or -2 and are therefore psi-2 or psi-4 objects. We will also encounter energy momentum formations that have a length dimension of -2 and are therefore psi-4 objects, meaning they are made up of 4 basis spinors. What you should also know about these two equations is that the coupling constant is dimensionless, which is why the theory presented here is renormalizable, and that we have deliberately omitted the gamma algebra, as carrying it through, especially in higher product formations, would be detrimental to readability. Now we simplify the equations a bit more by hiding the quotient on the left-hand side. If you have understood the fundamental interaction shown here, then you have essentially understood the core of the theory already, because with these two equations we have now created the theoretical foundation with which we can describe the entire process chain, both before the Big Bang, during the Big Bang and after the Big Bang. And this brings us to the next step, the construction of the preformation structure. We already know the first step. It shows the fundamental interaction itself. Since in the following construction process we will create a complex, point-split separated local environment around the interaction point x, we have to distinguish between several point splits. We call the first point split xi, and we get d xi psi of x is equal to psi of x minus xi, psi bar of x, psi of x plus xi. We call this product psi-3 because it is a product of 3 basis spinors. As long as xi is unequal to 0, we are in the already mentioned system opening phase. In this phase, each individual basis spinor is again subject to the basic dynamics, which thus drives the construction process forward. The basis spinor psi of x minus xi, split from the interaction point x, is therefore also subject to the basic dynamics, which is initiated here by d rho. We obtain psi of x minus xi minus rho, psi bar of x minus xi, psi of x minus xi plus rho. We proceed in the same way with d lambda and psi of x plus xi, which gives us psi of x plus xi minus lambda, psi bar of x plus xi, psi of x plus xi plus lambda. And with d eta and psi bar of x, we get psi bar of x minus eta, psi of x, psi bar of x plus eta. The psi3 has now become a psi9, meaning a product of 9 basis spinners. In the next step, the individual basis spinners will be sorted according to their effective distance from the interaction point x. Figuratively speaking, the basis spinner psi of x minus xi plus rho is closer to the interaction point x than psi bar of x minus xi, psi bar of x minus eta, or psi of x minus xi minus rho, which is the split furthest away from the interaction point x. The same applies to the basis spinner psi of x plus xi minus lambda, which is closer to the interaction point x than psi bar of x plus eta, psi bar of x plus xi, or psi of x plus xi plus lambda, which is the split furthest away from the interaction point x. Now, sorted, the psi9 looks like this. We are still in the system opening phase. The interaction point x has been split at 3 additional points, and for each of the point splits xi, rho, eta and lambda, it applies that these are unequal to 0. The individual 9 basis spinners are again each subject to the basic dynamics from the beginning, which further drives the construction process. It follows d epsilon 1 and psi of x minus epsilon 1, psi bar of x, psi of x plus epsilon 1, d epsilon 2 and psi of x plus xi minus lambda minus epsilon 2, psi bar of x plus xi minus lambda, psi of x plus xi minus lambda plus epsilon 2, d epsilon 3 and psi bar of x plus xi minus epsilon 3, psi of x plus xi, psi bar of x plus xi plus epsilon 3, d epsilon 4 and psi bar of x plus eta minus epsilon 4, psi of x plus eta, psi bar of x plus eta plus epsilon 4, d epsilon 5 and psi of x plus xi plus lambda minus epsilon 5, psi bar of x plus xi plus lambda, psi of x plus xi plus lambda plus epsilon 5. We are almost done. Now we develop the left side with d epsilon 6 and psi of x minus xi plus rho minus epsilon 6, psi bar of x minus xi plus rho, psi of x minus xi plus rho plus epsilon 6, d epsilon 7 and psi bar of x minus xi minus epsilon 7, psi of x minus xi, psi bar of x minus xi plus epsilon 7, d epsilon 8 and psi bar of x minus eta minus epsilon 8, psi of x minus eta, psi bar of x minus eta plus epsilon 8, and d epsilon 9 and psi of x minus xi minus rho minus epsilon 9, psi bar of x minus xi minus rho, psi of x minus xi minus rho plus epsilon 9. Psi9 has now become a psi27, meaning a product of 27 basis spinners. Written side by side, the spinner product is hardly readable, which is why we want to use a new form of representation. The individual point splits that belong to a basis spinner are now no longer in brackets, but written one below the other. The interaction point x is marked in the middle. Since we are still in the system opening phase, that is, in a point split separated local environment consisting of 13 point splits, each of which is unequal to 0, we want to blur this environment, symbolized here by the extended circle. We now have a psi27 in the point split separated local environment x sigma 13 with sigma 13 unequal to 0, where sigma 13 stands for all 13-point splits involved. Later, we will take a closer look at the system closure phase, symbolized here by a sharp representation of the interaction point X. In this phase, each of the point splits in the point split separated local environment X sigma 13 tends to 0 and eventually reaches 0 in the limit. But now back to our still open system. Psi27 is an unstructured product consisting of 27 basis spinners. To give structure to the Psi27, we need a structuring process. This consists of subprocesses for separation and binding, because if you want to structure a set, you can do so by separating something from something else or by binding something with something else. Let's start with separation. We need energy momentum, which must be contained in our Psi27, because there's nothing else in the fundamental construction process. Structuring energy has a length dimension of -1, just like structuring momentum. Since the length dimension of a basis spinner is -1/2, we are looking for a Psi4 object, highlighted here in light blue. This energy momentum takes effect and is incorporated into the Psi27. We mark the points where the energy momentum takes effect with a zigzag symbol, the symbol for separation. The unstructured Psi27 has now become a semi-structured Psi23. We proceed analogously with binding. We need an energy momentum, which must also be contained in our spinner product. So we are again looking for a Psi4 object, visible here in light blue. This energy momentum also takes effect and is incorporated into the semi-structured Psi23. We mark the points where the energy momentum takes effect with a binding symbol. The semi-structured Psi23 has now become a structured Psi19, a product of a total of 19 basis spinners, which we refer to as the preformation structure. Now it also becomes clear why the Psi9 had to evolve into a Psi27 first. The structuring foundation, consisting of a total of 8 basis spinners, would simply not have had any remaining set of basis spinners within a Psi9 that it could have structured. This completes the second step. From this preformation structure, the primordial universe develops in the next step, which, as already mentioned in the overview, consists of a total of 6 particles. Let's take a closer look at how these 6 particles develop. In the center we see a Psi3 object, a spinner product of 3 basis spinners. This contains the point split epsilon1. This point split is now closing in the system closure phase, thus tending to 0, and is therefore consumed, meaning it cannot act in other objects that may also contain this point split. This isn't the case here anyway, since epsilon1 only exists in the object highlighted in blue. Epsilon1 is now closed and Ni3 has formed as a result. This is a fermion consisting of 3 basis spinners with the canonical length dimension of -3/2. It is therefore an observable particle which has a substructure of 3 non-observable basis spinners. Next, another object becomes visible. A spinner product consisting of 4 basis spinners. It contains the point splits Xi, Rho, Lambda, epsilon6 and epsilon2. These point splits close and are also consumed, meaning they can no longer be used anywhere else. Let's look at this step by step. We start with Xi, followed by Rho, Lambda, epsilon6 and epsilon2. After these 5 point splits have closed, the G bar 5 forms. This is a boson consisting of 4 basis spinners with a length dimension of -2. It is therefore also an observable particle with a substructure. The next object is a spinner product of 2 basis spinners. It contains the 2 point splits epsilon 7 and epsilon 3. We call the resulting particle R2. This is a boson consisting of 2 basis spinors with a length dimension of -1. Between the separating elements, we see another object. It is a spinor product consisting of 4 basis spinors, which contains the 3 point splits eta, epsilon 8 and epsilon 4. We call this object G3. It is also a boson consisting of 4 basis spinors with a length dimension of -2. On the left side of the separation element, an object consisting of 3 basis spinors emerges. It contains the epsilon 9 as the only point split. It is therefore a one-split particle, which we call Ni1. It is a fermion consisting of 3 basis spinors with a canonical length dimension of -3/2. On the opposite side, to the right of the separating element, we see a similar object consisting of 3 basis spinors. It contains epsilon 5 and is also a one-split particle named Ni2. Ni2 is another fermion consisting of 3 basis spinors with a canonical length dimension of -3/2. We now use an even simpler notation by hiding the individual point splits and display the number of point splits involved via an index to the left of the particle symbol. Since the limit has been reached for all point splits, the system is now closed. We have used up all point splits and identified a total of 6 particles. For visualization purposes, we represent the closed system by sharply drawing the interaction point X. This is the primordial universe, a set consisting of 6 particles and highly symmetrical in structure. The point split distribution is maximally directed inward, meaning towards the interaction point X. Next, we will look at the properties of these 6 particles and what the point splits have to do with them. Properties result from the point split densities. It is therefore crucial how many point splits have contributed to the formation of the respective particle. We define that particles with a point split density of 0 or 1 are massless and have no charge. Particles with a point split density of at least 2 have mass. Particles with a point split density of at least 3 are additionally charged. Particles with a point split density of 4 have an additional mass layer, meaning 4-split particles are heavier than 3-split particles. Particles with a point split density of more than 4 are unstable, meaning they cannot form as elementary particles. Ni3 is a fermion that only contains the epsilon 1 split. This can reach the interaction point X unhindered during the system closure phase. The particle has no mass and is also uncharged. R2 is a boson which contains 2 point splits, namely epsilon 3 and epsilon 7. These interfere with each other during the system closure phase and cannot reach the interaction point X unhindered. Upon interference, point curvature around X occurs, resulting in the formation of mass. R2 is thus a massive boson. It is short-ranged and repulsive due to the internal structure of the basis spinors psi bar, psi bar. G3 is a boson which contains 3 point splits, namely eta, epsilon 4 and epsilon 8. These also interfere with each other during the system closure phase, forming both mass and charge. Due to the 3 independent point splits, the local point X is not only curved, but also squeezed, and this squeezing leads to a compression of the mass formed by the 2 point splits. This point squeezing creates charge. G3 is therefore a massive charged boson. It is short-ranged, attractive due to the internal structure of the basis spinors psi bar, psi bar, psi bar, psi bar, and charged with a gravitational charge Q0. G bar 5 is a boson which contains 5 point splits, namely Xi, Rho, Lambda, Epsilon 2 and Epsilon 6. These interfere with each other during the system closure phase, forming mass, charge and an additional layer of mass. G bar 5 is thus an extremely massive charged boson. It is extremely short-ranged, repulsive due to the internal structure of the basis spinors Psi, 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 and charged with a gravitational charge Q bar 0. It is also unstable due to the fifth point split. We will see what that means in a moment. Ni1 and Ni2 are also fermions, which contain only one point split and are therefore massless, just like Ni3. Here is an overview of all the particles that have evolved so far and belong to the primordial universe. In total, there are 3 massless one-split fermions, Ni1, Ni2 and Ni3, which are 3 neutrinos, 1 unstable 5-split boson G bar 5, a 2-split boson R2 and a 3-split boson G3. It contains 2 charged particles, namely G3 and G bar 5. The entire system is charge neutral. This completes the third step, the formation of the primordial universe from the preformation structure. Since we know that our present-day universe consists of more than the 6 particles we just identified, there must be a reproduction mechanism inherent to the primordial universe. We will now take a closer look at this. To do this, let's zoom back into our primordial universe. G bar 5 is unstable due to its 5-point splits and the associated extremely high mass. Figuratively speaking, G bar 5 breaks up into its constituents, and this in turn leads to the restructuring of the remaining set shown here. This means that the point splits open up and are thus available for particle formation again. Due to the breakup of G bar 5, we are back in the system opening phase, represented here by the blurred interaction point X. The 13 point splits which are now available again are shown here. But before we focus on that, let's take a look at the neutrino Ni1 in the center. This is pushed apart by the breakup of G bar 5, meaning the basis spinors are again separated and thus subject to the basic dynamics from the beginning, since they cannot exist independently. This means that each of these 3 basis spinors serves as a starting spinor for its own construction process. This construction process is analogous to the already known construction process, except that now 3 of these construction processes take place in parallel. For the sake of completeness, we add the starting spinor from the beginning. As a reminder, from this we first build up the preformation structure via the fundamental interaction and then develop the primordial universe through formation processes. This contained a massive, unstable G bar 5 boson which had broken. This led to the separation of the central neutrino and the restructuring of the remaining set. We represent all sets undergoing the breakup process with a small white box with a breakup line. From the 3 basis spinors, 3 new sets are thus created via the processes already known to us, each containing 3 neutrinos, a G3, a G bar 5 and an R2, and each undergoing the breakup process again due to the unstable G bar 5. The reproduction cascade mentioned in the beginning is set in motion. We see an enormous number of small breakup processes and the associated formation of many sets that go through the breakup process. At some point, the overall system becomes inert and sets are formed that no longer undergo the breakup process. These sets are represented here as small white boxes without a breakup line. The reproduction cascade comes to an end. We already know what happens to the G bar 5 and the central neutrino. However, what remains to be clarified is what happens to the remaining part of the sets that undergo the breakup process. Let's take a closer look at such a set. The breakup line crosses the central neutrino Ni1, G-bar 5 and R2. The breakup of the G-bar 5 leads to the separation of the central neutrino. We already looked at that. The remaining part of the set will be restructured and forms anew. As we can see, we are once again in the system opening phase. From the right fragment of the G-bar 5, a massive scalar two-split boson initially forms. It contains the 2 point splits lambda and epsilon 2. This boson is commonly known as the strong interaction and is therefore abbreviated as ST. In addition, an energy momentum boson is formed, which is skew symmetric, that means parity asymmetric. It contains the epsilon 3 and epsilon 6 split and is thus also a two-split boson. On the left, we again see a Xi3 formation, a fermion containing a total of 4 splits, Xi, Rho, epsilon 8 and epsilon 9. It is thus a massive and charged fermion, which we call P+, and which is commonly known as the proton. On the right, we see a Xi3 formation, also a fermion, which contains a total of 3 splits, eta, epsilon 4 and epsilon 5. It is thus a massive and charged fermion, which we call E- and which is commonly known as the electron. A Xi4 formation remains, which contains only the epsilon 7 split. This is a massless boson that is uncharged, long-ranged and extremely weakly attractive. It is the graviton. Under certain energetic boundary conditions, the energy momentum boson splits into 2 connected bosons, one of which is a massive short-range 2-split boson, which contains epsilon 3 and epsilon 6, and which will be abbreviated as Z. And the other is a massless long-ranged boson that does not contain a point split and is denoted as gamma. This gamma is also known as a photon. Together, these bosons form the electromagnetic weak interaction. The system is now closed again. What we see here is the familiar set of normal matter. Analogously to this set, antimatter can also form. In such a set, E+ is formed on the left side and P- on the right side. It is also worth noting that in a set undergoing the breakup process, the point split density is maximally directed outwards. We again use a simpler notation by hiding the individual point splits and displaying the number of point splits involved via the index to the left of the particle symbol. Here is a complete overview of all particles and their properties that belong to the set of normal matter. So we can conclude that every set that undergoes the breakup process develops into sets of normal matter as well as antimatter via specific formation processes. Now, what about the sets that do not go through the breakup process? Let's look at this together. Initially, the same particles are formed: a central neutrino Ni3, the G-bar 5, the G3, the R2, and 2 further neutrinos Ni1 and Ni2. Due to the inertia of the entire system, the G-bar 5 no longer breaks. Instead, a stabilization process takes place. The R2 transfers its 2 splits, epsilon 7 and epsilon 3, to the G3. The G3 becomes a G5 and the R2 accordingly an R0. The second phase of the stabilization involves the G-bar 5 transferring the point split Xi to the Ni1, which becomes a massive 2-split neutrino. The G-bar 5 becomes a massive, repulsive, charged and stable G-bar 4 boson. The G5 transfers a point split, namely eta, to the Ni2, which also becomes a massive two-split neutrino. The G5 becomes a massive, attractive, charged, and stable G4 boson. The system is now closed again. It is also charge neutral. What we see here is the set of dark matter. It consists primarily of two extremely massive bosons, G4 and G-bar4, with extremely short-ranged gravitational and anti-gravitational interactions respectively. It also contains three neutrinos, two of which are massive. This set shows why dark matter can only interact gravitationally. The simplified representation is as follows. Here again is an overview of all particles and their properties that belong to the set of dark matter. Now we know what the reproduction cascade is, what triggered it, and what results it has led to. Sets of normal matter, antimatter, and dark matter have emerged. The next question is what the quantitative ratio between normal matter, antimatter, and dark matter was immediately after the reproduction cascade. To calculate this ratio, we sum up all sets that were created from level 1 to the penultimate level, meaning n-1, and can be assigned to normal matter and antimatter. We then sum up all sets that were created in the last generation stage of the reproduction cascade and are assigned to dark matter. If we now let n approach infinity, we obtain a quotient of 2, which corresponds to a quantity ratio between dark matter and normal matter antimatter of 2/3 to 1/3. This composition of the universe immediately after the Big Bang corresponds exactly to the space telescope measurements, such as the Planck measurement of March 21, 2013. Since this quantity ratio had developed directly after the Big Bang, a shift in the proportions could be observed shortly after the Big Bang, shown here as approximately 380,000 years after the Big Bang. The proportion of dark matter, as well as the proportion of normal matter antimatter, had decreased minimally. This shift becomes even clearer when we look at measurements of the composition of the universe today. The proportion of dark matter is still around 26.8%. The proportion of normal matter antimatter is just 4.9%. In contrast, with the decline of these two components, the proportion of dark energy has increased significantly. It has risen from an original 0% to 68.3%, making it the largest component in our universe. We now look at what has led to this shift in the components of the universe. Responsible for this are annihilation processes, meaning pair annihilation processes of normal matter, antimatter, and dark matter. Let's start with normal matter and antimatter. Electrons and positrons are each three-split particles. When these collide, restructuring occurs. A total of 3 new objects are formed. 2 of these objects shown here on the left and right are one-split bosons. We call the one on the right E1. Under suitable energetic boundary conditions, it can split into 2 identical formations. These are 2 photons, meaning a gamma pair. This effect is well known. On the left, we see a massless, long-ranged, one-split boson with an attractive force. Of the original 6-point splits, the remaining 4 form the third object, which is shown here in the center. This is a 4-dimensional space-time quantum. The pair annihilation of the proton and antiproton takes place in a similar way. Protons and antiprotons are each 4-split particles. If a proton and antiproton collide, restructuring also occurs. A total of 3 new objects are formed, 2 of which, shown here again on the left and right, are one-split bosons. The one on the right is also called E1. This can also split into 2 identical formations under suitable energetic boundary conditions. Again, also in 2 photons. On the left-hand side, another massless, long-ranged, one-split boson with attractive force is created. Of the remaining 8-point splits, the remaining 6 form the third object, shown in the center. This is a 4-dimensional space-time quantum, which contains an integrated 2-dimensional SU2 structure, the so-called isospace. Finally, there remains the pair annihilation of the G-bar 4 and the G4, the two massive bosons of dark matter. The restructuring looks like this. A total of 3 new objects are formed, 2 of which, shown here again on the left and right, are identical one-split bosons. We designate both as E2. From the original 8-point splits, the remaining 6 form the third object, shown here in the center. Once again, a 4-dimensional spacetime quantum has emerged, which also contains an integrated 2-dimensional SU2 structure. Here is an overview of the two end products, which we've labeled E1 and E2. These are 2 bosons, each with a coupled 4-dimensional spacetime quantum and a partially integrated 2-dimensional SU2 structure, the isospace. What is interesting is that spacetime is not an a priori property of the universe, but a secondary product created by annihilation processes. To summarize, we can state that we have succeeded in developing a dynamic foundation with which we can describe the entire process chain before the Big Bang, during the Big Bang, and after the Big Bang. This foundation consists of the simplest, nonlinear interaction, which is capable of developing reality as we know it today through several fundamental processes. The preformation structure, which initially develops from the fundamental interaction, provides the blueprint for the primordial universe. This contains the unstable G-bar 5, which breaks and triggers the reproduction cascade. At the end of the reproduction cascade, elementary particle sets of normal matter or antimatter and dark matter are created. The continuous change in the quantitative ratio of the components of the universe can be explained by annihilation processes of normal matter, antimatter, and dark matter. These produce elementary particles of dark energy with a coupled 4-dimensional spacetime structure. Spacetime is thus created by releasing the point splits that are not bound to either of the other 2 end products of the annihilation processes. The preformation structure not only provides the blueprint for the primordial universe, but also encodes all other components of the universe of today. It also enables predictions to be made about what the still unknown part of the universe might look like. Thank you very much for watching.